All right, so we are here doing the live lecture for week 5 in your course. This is just a sample course, so this might look a slight different than yours, but you probably have an announcement somewhere. You might have to click on your actual announcements to see it if it's a past announcement and not one of the top 3 in your course, or you might see a link there on your homepage of your course to the live lecture schedule. So I just want to call attention to what we're going to talk about today. And so we are in week 5. So you can toggle this little menu over here to see an outline and can easily scroll until you see week 5 instead of having to scroll through the whole thing repeatedly. And so you can see that the topics for this week, sections 4.3 and 4.5, section 5.5 and section 5.6. We are starting the new content that is going to be included with your midterm exam. And scratch that, final exam, because you have just last week taken your midterm exam. So this is moving forward with that. After the session, you can come back here and you can see there's already a recording from the Wednesday night session, and then these will get updated and become live links as today's session is held, and then as Saturday's session is also held. And then we have a student feedback link here to a form that we would really appreciate you filling out to give us your feedback, but also it lets us know you were here. And we share that with our instructors who are teaching the course, because some of them might be giving you some incentive that says if you attend these lectures, maybe you get something extra in the class. Maybe you get an extra attempt at a quiz or whatever your instructor may have offered you for that. So we do encourage you to use that if you're here live or also watching this in the recording. And I'll put that link up at the end as well. So we're going to get to the topics. So this is just a copy of what I just showed you in that live schedule. And I have this gap here because really they talk about 2 different things, but some of it is related. So in section 4.3 and 4.5, you're really focusing on quadratic functions solely. And those are a type of polynomial. So they're kind of like a special case. They're a degree 2 polynomial. And then you can see in section 5.5, it talks about polynomial as well as rational inequalities. So this section 4.5 with inequalities for quadratic specifically is actually quite similar to what you would be doing for polynomial inequalities. But there are some specific things about quadratics that are unique that isn't the same as every other polynomial. So there's some general content here related to that, and then using the graphing tool in my lab as well. And Wednesday's lecture actually focused a lot on that and a little bit of 5.5 and 5.6. I think I'm going to take a different tactic today, and I'm going to start backwards. I'm going to start with 5.5 and 5.6 and then work my way back to 4.3 and 4.5, just so that we get a broad coverage of things as well. And so in 5.5 and 5.6, this is focusing on polynomials, and then we throw a little bit in with rational inequalities. And those are things where they're not equal to, and they can either be greater than, less than, et cetera. And then some things with finding real zeros. So if I focus on section 5.5 first, when we have inequalities, we are talking specifically about having either a greater than or equal to, less than, or less than or equal to. And so by including or excluding with the equal to, we are allowing to change basically some endpoints of our intervals that we're including. And we are going to focus on mostly using interval notation. So anything that's going to end up having the equal to part for it. So if greater than or equal to, or less than or equal to, you might use brackets in some way, and those are the ones that look more boxy and kind of square. And then if instead just using greater than or less than, then you might only be using parentheses. Spell that correctly. And so those are nice curved enclosures. So that's one thing to bear in mind. And you've learned all about interval notation early on in the course. The things that I have in bold here are going to pertain to rational inequalities and not necessarily polynomial. So if something is rational, we want to make sure that means it's written as a quotient usually. We want to make sure that it's written as a single quotient. We wouldn't need to do that with polynomials because they're not quotients. We also want to make sure that we're finding the domain if it's a rational function. Because remember, polynomial functions have all real numbers from negative infinity to infinity as domain. So we don't have any restrictions with those. So again, the bold parts here that I've now highlighted in blue are, differences we would do with rational. And then, so you're looking to see, first off, that you have 0 on the right side of your inequality. So you'll notice in all of these statements there, 0 is on the right side. If it isn't, you move things around so that it is. And then once you've done that, you're going to solve the function equal to 0, because you're going to find those real numbers that are those solutions. And then, again, I'm going to highlight it in blue, but I have it in bold. If it's rational, you're also going to find out where your function's undefined, because again, you have a quotient, so you don't want the denominator equal to 0. So denominator, you don't want equal to 0, okay? Once you've obtained all your numbers in step 3 there, it says you're going to divide that into a real number line with intervals. So you're going to draw a number line, and whatever values you have, you're going to break that up into however many intervals you might need. So like here, I have this broken up into 4 intervals. I could break it up into 2, whatever is needed. And then what you're doing at that point is focusing on determining where in those intervals is your function positive or negative. So you might end up something like testing the first interval and getting something that's negative, testing the second one and getting something that's positive. Maybe you test the third one and that's also positive. Maybe you test the fourth one and that's negative, or whatever combination it ends up being. But you're testing that. And then you're paying attention to, well, which inequality do you need for the problem? Greater than or less than? And is it strict or not? If it's not strict, then you might not be including with brackets. If it is strict, you'll have differences with that, and we'll talk about that with an example here in just a second. And then you always want to, again, exclude values where the function is undefined, and so you want to make sure for those rational functions you pay attention to those differences. So that's kind of the overview, okay? And so if we take a look at an example here, make that bigger. All right, so I pulled this from our 5B homework. This happens to be problem 2, and you'll see something similar to this. You're given 2 questions. One is figure out where the function is less than 0. And so there is a less than sign there. And so we want less than 0. Well, think about what that means, okay? So this means below the x-axis, because the x-axis itself is the line y equals 0, okay? And so anything above that would have y values that are positive, and anything below that would have y values that are negative. So to be less than 0, the y values, which is what f of x represents, would be negative. So you're looking for what is below the x-axis, okay? So you'll notice that the instructions, it'd type your answer in interval notation, so like what I was just talking about with parentheses and brackets. And because this is just less than, it's strictly less than, so I'm not including equality. So I can't include anything on the x-axis, so it's strictly below. And so as I look at my function, which is in blue, and then because this is rational, you have these asymptotes, which are the dotted lines. I'm looking to see where are parts of my function in blue below the x-axis. So like I could trace over that. So it looks to me that this first curved part, all of it is below the x-axis, okay? And then it looks like on the other side of that first vertical asymptote, x equals -2, that the function is now above the x-axis. However, it looks like right about at the origin, it starts to be down below again. So if I've traced over there in pink, the portions that are below, and then when I get to the other side of the vertical asymptote x equals 3, I see the blue part of my curve for my function is now back up above the x-axis. So I've highlighted in pink the portions of my graph that are actually below the axis. Now I got to figure out, how do I get the solution for that? So remember, the solution consists of x values in intervals, saying you start from one x value to another x value along the x-axis, okay? So the way I like to explain this to my students is I think of it as, imagine you had a nice big flashlight, or the sun was below you. So you have a flashlight and it's shining light up from above. What shadow would it create along your x-axis for the portion of your function that is down below? Well, it would create a shadow of value, since it has an arrow going indefinitely to the left, that would go all the way to the left on my x-axis, and it would cover all these x-axis values up until, oops, I get to the vertical asymptote, right? That's where the curve takes a nosedive and goes down along the left side of that asymptote. So therefore, I can go up to, but not including that asymptote value, which is at an x value of -2. And so therefore, as an interval, that is from -infinity up to -2, but not including it. And so you can see that's the first part of our answer over here. So I already had the correct answers in here, and now I'm just kind of explaining where do those come from. Then the next part, there's a gap. So again, if I'm shining the light down here up on this, there's not going to be anything until it looks like I get to at the origin. So it starts there. And again, it goes all the way up until, oops, I get stuck at that next vertical asymptote, but not including it. And so that takes me through an x value of 0 up until it looks like 3, because that's where the asymptote is. So that interval that I just traced, that you can think of like a shadow being projected onto the x-axis from down below where your curve is from the open interval of 0 to 3. And it's open intervals because, again, that asymptote, I'm not including up to 3, but I'm not including 0 because it looks like that's right on the x-axis at 0, 0 at the origin. And remember, this is just simply below and not including equality with 0. And so therefore, I put those two things together with a union symbol, and that's how I get this first answer here, okay? Now, if, hypothetical, if we had f of x less than or equal, let me make that more clear that that's less than or equal to 0, how would our answer change? Well, I'm still covering the same portions below, but I'm looking at below and on the x-axis. And so the only place where it's on the x-axis would then be at that point 0, 0. So I would still have the first open interval from -infinity to -2 union with, but now here's where the big change is. I would have a bracket of this 0 instead of a parenthesis over to 3. So by just changing the inequality sign, I've got almost the same work. I'm just changing the closures around it, okay? Same thing over here. Then if I go with part B, where is f of x greater than or equal to 0? But to think about, what does that mean? This means above or on the x-axis because of the equality, okay? So now if I come over here and trace, I'm going to get rid of what I had for the first part. I come over here and trace, where is it above or on? Then I'm looking at this upper part of the curve to the right side of x equals -2 down to and including, so I'm going to kind of put a solid dot here, and including on the x-axis. And then again, in this part to the right side of the second asymptote, x equals 3. And then that's going to go off indefinitely. So if I think of, again, now maybe instead of flashlight, maybe it is literally our sun casting a shadow down onto the x-axis, it would cast a shadow just to the right side of x equals -2 over and including 0. So there's our -2 to 0 with a parenthesis around -2 and a bracket around 0, because we're now including that point on the x-axis. And then if I move the sun over, and I'm still casting a shadow over here on this other part that I highlighted down onto the x-axis, I'm looking at just to the right of x equals 3, but then going on indefinitely to the right, and hence that is open parenthesis 3 to infinity. Remember, infinity is always with parentheses. If this was polynomial, I just wouldn't have asymptotes on my graph, but I'm still focusing on what is above, what is below, or what is on my axis, or the x-axis with that, okay? So that's kind of interpreting it through a graph, okay? Sometimes the graphs are provided to you and then you just interpret it from there. And again, you are welcome to ask questions if you have any in the chat, or to virtually raise your hand. So the next problem, I'm going to actually go into a live MyLab screen to do this. This one is going to be solving rational inequalities, which is similar to what I just did, but not from a graph. And it's something where you could have intervals as a solution, but you might also have what we call isolated points as a solution. And I want to talk about what that means, because that's sometimes really confusing to students, because it's maybe not something you've ever seen before. So, so 19, section 5B. So my 5B homework, and question 19 is the one I think I selected earlier. Talk about. Okay. So this is the problem that we have, and this one is one of the setup and solve problems. So like if I move forward, like there's probably some that aren't set up and solved. Like this one's not set up and solved. Like 21 doesn't prompt you to actually put in all your intervals and what you tested. It just prompts you for the final answer, okay? But to do that, you should be doing what is prompted in these setup and solve problems, which is creating your intervals, testing it for positive and negative. Basically what I showed at the beginning back here in my overview of the process of what we're going to do and how we're going to draw that number line and then test those intervals. That's what I'm going to walk through. So this is the problem that we have, okay? So I'm going to just take a quick screenshot of this so I can put this on the screen where I can write on the screen more easily. And then we'll come back and enter the answers into MyLab. So here's that problem, okay? And so a couple things that I want to pay attention to. One is that it is telling me to, my pen is stuck for a moment. Forgive me. Not happy with my copy and paste, I think. See if I can change that. I apologize. Being a little finicky. Give me one moment. Okay, there we go. Now it's active. Sorry about that. Okay, so it does want us to type our answers in interval notation. It also says to use ascending order. In other words, we're working from left to the right, just like we would look at a number line from left to right. So this one is rational. I know it's rational because it has a numerator and a denominator. And so when I look at that with the numerator and the denominator, then what I want to focus on is, first of all, setting the numerator equal to 0, because that's going to find our real zeros. So I'm going to do this in stages. So I'm going to set, I'm abbreviating here, numerator equal to 0. So I've got 3 different factors in the numerator. I've got x squared, I'm going to set that equal to 0. I've got 5 plus x, I'm going to set that equal to 0. And I've got x plus 6, I'm going to set that equal to 0. And so I'm going to solve each one of those. So I can take the square root, get x equals 0. I can subtract 5, get x equals -5. And I can subtract 6 and get x equals -6. And so therefore I have 3 solutions there. Those are all my real zeros of my function, okay? In other words, real zeros are also your x-intercepts on your graph. And so those mean the same thing. And then the second part, because this is rational, is I want to focus on the denominator. I want to find out, where is my function undefined? So where is f of x undefined? And I'm calling all of this f of x on the left side. And it is with 0 on the right side. Remember, one of the first things to do was to make sure you've got 0 on the right side. This one does. If I had something on the other side that wasn't 0, I would subtract it over to the left side, and I would make a common denominator to make sure I have got one single quotient. And I talked about that at the beginning. So where is it undefined? That is where you are going to set your denominator, and again, I'm abbreviating, equal to 0. And so that is 2 factors of x plus 7. I don't need that parenthesis. Set that equal to 0 and set x minus 2 equal to 0. So I solved both of those and I got -7 and +2. Now, what does this mean? This is where the function is undefined. So we don't want to include these values at the end, meaning we are going to not use brackets for these, okay? Because that's where my function is not defined, the point like doesn't exist, so we can't include that. Now, why is that important? Because over here, my solution I'm looking for is greater than or equal to. So greater than or equal to means above or on, or on x-axis. That's what we're looking for the greater than or equal to. However, I am not, for the on the x-axis part, I'm not going to use -7 and 2, but I might have other values depending on what's going on for my real zeros that I have. So now I set up my number line. So if I've got a number line, just a horizontal number line, I now mark these from left to right in ascending order. So -7 is the smallest, that's on the far left. Then I see -6. Then I see -5. Then I would get to 0. And I'm just approximating where that would be. These are not exactly to scale. And then I would see 2. So I have a total of, if I number these, I have 1, 2, 3, 4, 5, 6 intervals. And if you look up here, there's 1, 2, 3, 4, 5, 6 answer blanks for intervals. So that kind of leads you to go towards that. So if I had solved all these values for setting the numerator equal to 0 and the denominator equal to 0, and I didn't have the same quantity of intervals that was the answer blanks, that's a clue to me that I did something wrong. But that all matches up. So I'm going to erase those numbers from 1 to 6 because I don't need those. I'm just emphasizing how many I have. So now it says list the intervals and sign in each interval. So I can go in and list these intervals. So my intervals would go in this answer blank with parentheses. They would all be parentheses. So I'm going to have negative infinity to -7. Then I'm going to have -7 to -6. And that would be inside the box. And then I'm going to have -6 to -5. And then I would have -5 to 0. And then I would have 0 to 2. And then I would have 2 to infinity. Again, inside the box. Now I need to test that. So back over in my lab, that little toggle there is a drop-down menu for choosing either positive or negative. Okay. So while I'm here, I can type in my intervals real quick. So you can type it in from the keyboard, or you can use this icon down here that gives you the template for that. So remember we said this was negative infinity, and you've got the infinity symbol down here on your template. And then I'm going to move my cursor over with the right arrow to put in, we said -7. And notice how that did not go in the blue box. So I need to fix that. So I didn't have my cursor moved over enough to put the -7 in the box. Now the blue box is gone. If you don't move that blue box out, if you've accidentally typed it in front of it, I think it might count the answer wrong. And you're going to look at it and you're going to say, well, it looks like I typed the right thing. Why is it wrong? Because it's not quite in that template. So then I can put in the next one. We said was -6, move my cursor over into the blue box, or I'm sorry, -7 to -6. Then I can do the next one we said was a template of -6 to -5. And see there, I missed the box again. So I'm going to delete that and get my cursor moved over. And there's the -5. So be very careful with that. And then we went from -5 to 0, I believe. My cursor over. And then we went to 0 to 2. And then 2 to infinity. And I need my template. There we go. So now, going back to the page I can write on, what we're going to do is we're going to pick any value that fits inside those intervals, and we're going to test it in the function to see if we get something positive or negative. So maybe in the first interval, I pick something to the left of -7. So maybe I can choose something like, let me do this in a different color. I can do something like f of -8. And then between -7 and -6, I can do f of -7.5 or 6.5, excuse me. And between -6 and -5, I'm going to just bump it down so you can see it better. F of -5.5. Between -5 and 0, maybe I do f of, I don't know, -1. Between 0 and 2, I do f of 1. And then 2 to infinity, I can pick anything. Let's just go with f of 3. So I figure out, and let me write this one clearer, the -8. So I figure out if I substitute all those in, do I get positive or negative for f of x? And that's using my function that I boxed in here in black. Now you can put this in your calculator, or you can just kind of reason it out as to, is each factor going to give you something positive or negative? So like if I have -8 and I'm plugging that in everywhere I have an x in my original function, each of those factors is going to be positive or negative. If I have -8 and I square it for x squared, it's positive. So I'm going to have positive, a -8 plus the 5 is going to be negative, a -8 plus 6 is going to be negative. If I multiply a positive, a negative, and a negative, that whole thing is positive on top. On bottom, a -8 plus 7 is negative. A -8 minus 2 is also negative. If I multiply those together, that's positive, and then I divide that, the overall result is positive. If you prefer not to do it that way and you want to take the time to try and enter all of that into your calculator, you can. But those of you who might be like stressed for time at the test, you have to decide like which one's going to be faster for you. Okay. So that's the first interval. If I do the second interval, and I'm going to get rid of my box there. I do the second interval, -6.5. If I square that, again, that's positive. -6.5 plus 5 will be negative. -6.5 plus 6 will be negative. So the whole thing up top will be positive. -6 plus 7 will be positive. -6.5, I meant to say 6.5 on the last one. Minus 2 is negative. So that product is negative. And then if I divide the positive and negative, now this is negative. And I keep doing that. So -5.5, I'll adjust all my signs. This will be positive for the top. -5.5 plus 5 will still be negative. -5.5 plus 6 will be positive. So there's one negative. So the overall top will be negative. On the bottom, -5.5 plus 7 will be positive. -5.5 minus 2 will be negative. The overall product is negative. So when I divide top and bottom, negative, negative, I get positive. Continuing down the line. So this does take a little bit of time, but it would take a little bit of time to type it into your calculator too. If I have -1, square it, that's positive. Plus 5 is positive. -1 plus 6 is positive. Top is positive. -1 plus 7 is positive. -1 and minus 2 is negative. So the overall, that's negative. So divide that, that's negative. If I use a +1 in the next interval, squaring it is positive. 5 plus 1 is positive. 1 plus 6 is positive. Top is positive. The bottom, 1 plus 7 is positive. 1 minus 2 is negative. The bottom is negative. Divide that, you get negative. Notice it doesn't always follow a pattern you might think it is. Notice this went positive, negative, positive, negative. Someone might think, oh, the next one will logically be positive, and it wasn't. It's negative. And then I plug in 3. This will be the last one. I check my signs. So 3 squared is positive. 3 plus 5 is positive. 3 plus 6 is positive. The top is positive. 3 plus 7 is positive. 3 minus 2 is positive. The bottom is positive. So if I divide those, it's positive. So I can now go into MyLab and I can select the toggles appropriately for positive, negative, then negative, positive. So positive, negative, positive, negative. And then this is, remember, where the pattern kind of broke. Negative, positive. I can check that. Fantastic. Then it's going to prompt you for the answer. Okay. So let me come back over to here. So if this is one of those open-ended questions, you would not have entered all of these intervals in the positive and negative, but you still would have done that on your paper. That would be excellent work to show your instructor when you submit your work after your test, for them to be able to check that, to know that you're doing the process right. If it's one of the open-ended questions, you type in your answer and you're not going to have a multiple choice. So that's why I kind of quickly left that screen, because I don't want people to just rely on the multiple choice, because the open-ended ones won't have multiple choice. So now we have to think about, well, which answer would we give for a final conclusion here? So remember, we had positive, negative, positive, negative, negative, positive. So our original problem was greater than or equal to, which we determined was above or on the x-axis, but we do not want to include -7 or 2. So we are not including -7 and we're not including 2. So think of those like open points on the number line, even though they're actually asymptotes, but on the number line, I'm putting them as open, so we're not going to include that. And I need everything above. So that would be this first interval, so -3 to -7. it looks like it would be this interval from -6, -5. And then it looks like it would be not including 2 and going to infinity. But that's all the above part. But the on part would be that, remember I had these real zeros, those are on the x-axis. So -5, so I would have to have a bracket here, and -6, I could have a bracket here, but -7, I'm not including, so like that would be a parenthesis. And then the 2 is not included, so that would be a parenthesis to infinity. But then I have to include just the point at 0. So there would be just a solid filled in point that I can include there. So I have to talk about how do I include that? So writing these intervals of what I just highlighted, this would be negative infinity, up to, but not including -7, so parenthesis, union, the next interval that is going to use brackets because we want to include -6 and -5 because those are real zeros and they're on the x-axis. Union, and then now here's the conundrum. What do I do with that single point 0? This is an isolated point. We include it as a set. So the set is just a list of items in braces. So isolated point, you're going to use braces. And those are the curly enclosures, or the fancy enclosures, I call them, the wavy ones, okay? So you're going to union in just that single point as a set, and then union the last interval that we said was not going to include 2, so that's a parenthesis to infinity. So if we did this right, that should be one of the multiple choice answers. But again, if this was an open-ended question, I would be typing that all in, okay? So going back to our answers, I see that B does not have an isolated point, so it's not going to be that. A, C, and D have isolated points, so I have to look very closely at the enclosures. So I don't want to include 7, or excuse me, -7, so it's not A. We already said it's not B. So I look at C and D. So C and D are the same, except for -6 to -5. One of them in C is with parentheses, and the other one in D is with brackets. So remember which one we had. We wanted brackets around the -6 and -5. So I believe the answer is D. And there we go. All right. So you really got to think about, again, what is above, below, or on the x-axis. And then because this is rational, you wouldn't have this extra condition if it was polynomial. You have to consider where it's undefined. So even though the inequality sign says to include, because of the equality sign, we actually have to exclude some points because that's where the function's undefined, okay? So again, questions are welcome if you have any, but that's how I would approach a problem like that. Okay. Excuse me. Section 5.6 continues to talk about polynomials. I know the last 2 examples I talked about were rational, but again, if you had only looked at the numerator of the last problem, that would be polynomial. And if you looked at a graph, you just would have a nice smooth continuous curve and you wouldn't have asymptotes, but you would still be looking for where is that function above or below or on the x-axis. And you just wouldn't have any domain restrictions. So continuing with polynomials, we talk about real zeros. Well, I used the real zeros in the last problem, right? I talked about how if I set the numerator equal to 0, that's really finding the real zeros of the function, or that is the same thing as like x-intercepts on the graph. So we're continuing with that idea here in section 5.6. So there's a lot of things in this section for rules, and I just have a few of them copied here. I'm not going to read all these, but the important things in this section to utilize to solve some of these problems are this remainder theorem, where if you're dividing by a linear factor, x minus a number c, you can find out what the remainder is by just evaluating your function at that appropriate c value. Once you know that this linear factor x minus c is a factor of your function, that would happen only if and only if you find out that that remainder, f of c, is actually 0. Basically, that means it divides equally. When there's no remainder left, you get a remainder of 0, you have found a factor of your function. And so those go together here, that if you, in one, if you find out that the function evaluated at c is 0, then that concludes that x minus that c is a factor. And then if you flip that around, if you know x minus c is a factor, well, then you know that the remainder must be 0, which means if you evaluate the function at c, it is 0. In total, the number of real zeros a function can have is no more than its degree. So that's really important. So it cannot have more real zeros than its degree. So let's say I have a degree 4. Then I have no more than 4 real zeros. I can have less, but I can't have more, okay? And then we have something called Descartes' rule of signs. This isn't always required, but sometimes you might find it helpful. You can actually do problems without Descartes' rule of signs, but it's another tool in your toolbox that you could use to help you with polynomials. And I think I have an example that'll go along with it. Basically, it tells you how many of your real zeros are positive and how many of your real zeros could be negative. So it just kind of separates them into two groups. Instead of saying, well, I've got all these real zeros, I don't know, some of them might be positive, some of them might be negative. This kind of narrows it down. So again, not strictly required, but you will have some problems that involve it. But you could do a whole problem and not consider Descartes' rule of signs technically. Rational zeros theorem is also one of those things that is another tool in your toolbox that can be really helpful. What it does is it narrows down the list of like infinite numbers that could potentially be your real zeros to a finite list of numbers that could be your rational zeros. And remember up here, we said you're not going to have any more than what the degree is for your real zeros. This is rational zeros. And remember, in the big scheme of things, say this whole box is my real numbers. Your real numbers are split in such a way, and not necessarily evenly, that you've got irrational and then rational. So remember, rational are contained within the whole set of real. So if you can identify the rational zeros, but you know you have a certain quantity of real zeros, well, then you can kind of deduce how many other ones must be like irrational that are kind of left over. And it helps narrow down the playing field. The important thing to remember in this is you have a polynomial that's nice and long. Excuse me. You're getting things from different places. The p, that is the numerator of this calculation, comes from the end. It comes from the factors of the constant. So this is the constant at the end. And the q is a factor of the beginning, which is your leading coefficient. And it generates a list in lowest terms of potential rational zeros. So it narrows the playing field. And so we can go through a process where you can figure out how many maximum real ones could you have, use Descartes' rule of signs to say which are positive, which are negative. You can use the rational zeros theorem to come up with a finite list of potential rational zeros. And then you can test them. And how you can test them is through substitution, which is really basically your remainder theorem. when we say substitution. Or you could do synthetic division, or you could do polynomial division, which almost nobody does, to find what you need. But here's the other thing I want to encourage you to consider. Don't forget factoring techniques. So if you have a 4-term polynomial, I recommend that you try factoring by grouping, because that's a skill you should have, and it's just another part of your toolbox. And if you can do that, it might work faster than these other things. And then there are a few other odds and ends with theorems and things, but in the time that we have, let me look at what I want to choose to use. Okay, so we won't have time to do all of these. Let me show you. Okay, I'm going to pick this number 29. I'm going to incorporate Descartes' rule of signs in problem 29, which would be similar to problem 27. But since we're short on time, I'm going to incorporate it all into one problem. So this says to use the rational zeros theorem to find all the real zeros of the polynomial. And then it says to use those to factor this over the real number. So there's two parts to this. Make sure you understand the difference when you read the instructions between finding the real zeros versus factoring the function. So notice I already, again, have the answers here, and then I'm going to walk you through how to get the answers. Finding the real zeros or finding the solution in the next problem that we won't have time to go over, the directions say to find the real solutions. That's the same thing as finding real zeros. So the directions might be phrased differently, but you're doing the same process, okay? So this one says to find the real zeros in the first part, and the second part is to factor it. If you know one, you know the other. And to use the rational zeros theorem. So first off, I'm just going to notice that if I was doing Descartes' rule of signs and the total number of possible real zeros, I'm going to do that off to the side. My potential max number of real zeros matches my degree. So 4 is my degree. So therefore, the max number of real zeros I could have is 4. And you can see the answer there has 4 real zeros. So I have not exceeded my max. Then Descartes' rule of signs. So again, I'm adding this to this problem because it could be helpful, but you don't have to use it on every problem. But I'm just kind of combining previous one to this. So what you do is you count your sign changes for your original function. So if you want the number of positive zeros that you could have, what I'm going to do is look from term to term from left to right. Technically, there is a plus sign in front of the x to the fourth. Excuse me. And so I'm looking for sign changes. So from x to the fourth to 10x to the third plus plus, it doesn't change. But from plus to minus, that does change. And then from minus to minus, from the squared term to the x term, that's no change. I apologize. And then from negative 40x to 44x, that is a change. So there's 2 changes. So there are 2 changes in the sign. So the possible number of positive, excuse me, I abbreviated there, zeros is 2, and then here's the tricky part, or start counting backwards by 2. So I'm either going to have 2 positive zeros, or if I count backwards by 2, I get to 0, I can end up with none. But what this tells me is that I'm not going to have like 1. and I'm not going to have 3. So I either have none, or if I do find 1, I know that I should keep looking because there will be a second one because I either have 0 or 2. Okay. Then for the number of negative, and again, I'm abbreviating here, zeros, I do something slightly different, but also similar. I have to evaluate f of negative x and then look at the sign changes. So I'm putting in a negative x. And then I'm going to simplify that. So if I raise it to the 4th power, this is really just positive x to the 4th. If I raise to the 3rd power, that makes this term negative 10x cubed. If I square a negative, it's positive, but I still have minus 15 for the coefficient, so it's negative 15x squared. If I have negative x times negative 40, that's positive 40x, and then the plus 44 doesn't change. Now I look for those sign changes. So from the beginning, positive to negative is 1 change, negative to negative is no change, negative to positive is another change, positive to negative is no change. So again, I have 2 changes. Now they're not always the same. These ones turned out to be the same. So I have 2, or you count backwards. Now, hypothetically, let's say I counted and I only had 1 change. Then my answer would just simply be 1. Or what if hypothetically, I did have another change. So say this was a negative sign. So then I've got a change here and a change here. If I had 3, I count backwards by 2, and then I could have 3 or 1. So I'd have all 3 of those, or I'd have 1. So that's how you kind of use Descartes' rule of signs, okay? The rational zeros theorem, which this says to use, is you have to come up with a list of potential rational zeros, and we write them as P over Q. P comes from the last number. It's factors. So I need factors of 44. So plus or minus 1, plus or minus 44, plus or minus 2, plus or minus 22. And then I have to look for other factors. I don't think that's divisible by 3, but it is divisible by 4 and 11. So plus or minus 4, and I'm going to run out of room. I always do that when I write it that way. Plus or minus 11, and then I think that's going to be it. So plus or minus 22 we had, plus or minus 44. And I just like to put them in order. You don't have to put them in order. You can write them as pairs if you want. And, you know, I could have done the plus or minus 1 and the 44 together, plus or minus 2 and the 22 together, etc. That would have been fine. But you have to generate the whole list. Then on the bottom, the Q, the Q is the factors from the leading coefficient. And actually, I don't want to do the whole x to the 4th. It's just the leading coefficient, which there is an invisible 1 that I'm just going to write. So that is plus or minus 1. So I get that whole list. Then I start dividing them. So let's say hypothetically, excuse me, that I had another set of factors. Let's say I had plus or minus 3 and plus or minus 1. I would start dividing these. So I'd end up with a whole list that would look like plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 11, plus or minus 22, plus or minus 44, when I divide everything by plus or minus 1. But then in addition to that, I would divide everything by plus or minus 3. So I'd have plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, etc. And because I'm short on time, I'm not going to write the whole list. So that's hypothetically what I could have. But what I really have, since I don't have the plus or minus 3, is just this whole list. So these are my potential rational zeros. So my actual real zeros will only come from that list. So I could start testing them to see which ones work. So One way you can do this is with synthetic division. And so let's say I start testing +1. So I'm going to put +1 in a box, and I'm going to write the coefficients from my polynomial in descending order, including any skipped terms with a 0 from left to right. So that's going to be 1, 10, -15, -40, +44. And we bring down the first number, then we multiply by the number in the box that we're testing, and that's 1, and it goes into the next column. And then we always add down. So that's 11. Then I multiply by the number in the box I'm testing, that's 11 times 1, and then I add down, that's -4. And I keep repeating this. So then times the box number, -4, add down, -44, multiply the box number, next column, add down, I get 0. That's good. This is the remainder. And what this tells me is that I can break my polynomial into this works. This is a real 0, and that real 0 is a factor of x minus 1. So real 0 of 1 gives me a factor of x minus 1. And then the rest of it comes from here. I go in descending order. So this started with a power of 4. I start with 1 power less. So this 1 is a 1x cubed, and then plus 11x squared in descending order, and then minus 4x to the first power, and then minus 44. And then I can repeat testing on this remaining, it's called a depressed equation, or try factor by grouping. And we are at time, but what I would continue doing is finding all the zeros that work. And you can see that there are ultimately 4 of them. So I encourage you, like, maybe to finish out this problem on your own and see if you can get all those real zeros to work. And then each time you have a real 0, if x equals c is a real 0, then x minus c is a factor. And that's how you get these answers down here, all multiplied together. So we are out of time. If you want to come back and watch anything in a recording, or you want to fill out our survey, we would greatly appreciate that. Here is the link to the survey. I will put in our chat so that you can just click on it and fill that out if you like. And again, the recording will be back in the live schedule, probably no later than tomorrow. And there's another session tomorrow from 2 to 3. And if you want to see some more stuff about the section 4.3 and 4.5, there's some of that in the recording from Wednesday. So good luck, and we hope to see you back in week 6. Thanks for attending.